Thank you for the kind introduction, and thank you for having me in this excellent meeting. And today I will introduce you concepts about pulsatile hemodynamics called Ming energy pulsatility index. And here's my conflict of interest disclosure. And as you know, that high blood pressure is not just a number. They can cause various different kinds of target organ damage we call hypertension-mediated organ damage, such as brain, heart, kidney. And for heart, that's called LVHF, heart failure. For brain, it will cause cognitive decline or stroke. And for kidney, it cause renal dysfunction, proteinuria. Today, I will focus more on brain and the kidney. And as you know that vascular aging or arterial stiffness has been implicated in the pathophysiology of cognitive decline. Among them, vascular aging has proposed as important markers. And today we will focus more on the carotid hemodynamics. And because carotid artery is the conduit for the heart to pump the blood into the brain, with not only the oxygen but also nutrients, and the pulsatile flow, in contrast to the mean flow, the steady flow can cause damage to the brain. In our previous study, we demonstrate that with increasing blood pressure, that will associate with a higher proportion of cerebral small vessel disease. And not only the pressure, but also the flow is important. As you can see that with decrease in diastolic flow velocity in the carotid artery, there is a higher proportion of cerebral small vessel disease. In another study published in Stroke, we demonstrate that with increasing central systolic blood pressure, there is a higher incidence of stroke. And further, within each the same stratum of the central blood pressure, you can see higher carotid flow pulsatility index can cause higher risk of stroke. And there's a concept described in the possible mechanism on the organ damage, and that's called impedance mismatch. At a young age, the aorta is very elastic, compliant with low aortic input impedance, and the carotid artery had a smaller diameter and with a higher vascular impedance. Therefore, there is an impedance mismatch between two artery systems, and such a mismatch can protect the pulsatile flow generated by the heart into the brain. And with increasing proximal aorta stiffness, vascular aging, the proximal aorta will become stiffened, and that mismatch will become matching. Therefore, the pulsatile flow generated from the heart will more directly enter into the brain and cause the brain injury. And this phenomenon has been proposed, and today that we try to answer whether this is true in our populations. So we ask two questions: whether the altered profile of carotid pressure and flow waveforms have potential detrimental effects on cognitive function, and also we want to evaluate the aortic impedance mismatch associated with the carotid mean and pulsatile energy and with cognitive function decline. And to measure cognitive function, we use the MOCA. And MOCA is a questionnaire constituted by 20 items clustered into 7 subgroups. And that was conducted by face-to-face interview by our study nurse. And in our populations, we have 2 cohorts. One is CVD FACS, another one is last cohort. There were around 1,800 subjects enrolled in these studies. And how do we measure the hemodynamic parameters? Actually, we measure the aortic flow using the conventional echocardiography, and also we use the carotid probe to acquire the carotid flow waveforms. And also we use the applanation tonometry to register the carotid pressure waveforms. And also we calculate the carotid femoral pulse wave velocity as the arterial stiffness measure. And this is the most important concept figure in our study. And for aorta, and for both aorta and carotid artery, we measure the pressure waveforms and the flow waveforms. And by the products of the pressure and flow waveforms is the power waveforms. So as you can see, using the power multiplied by flow, that can generate the power. And with the integration over one cardiac cycle, we can transform the power into the energy. And we can calculate not only the mean energy, and also the pulsatile energy. So we can calculate the two components, pulsatile component and the mean component. And with that, we can also calculate the potential energy. And in these populations, the mean age is around 60 years old, and 1/3 of them are male. And as you can see, their blood pressure are pretty normal, 125, and the CAPW is 12. And as you can see, we evaluate the association of these hemodynamic parameters with cognitive function. And as you can see, that among all hemodynamic measure, including CAPW, the carotid energy pulsatility index, which is derived by calculating with the equation of pulsatile energy divided by mean energy. And of all these parameters, the carotid energy pulsatility index has the strongest association with MoCA score. And if we further separate it then into the pulsatile component and the mean component, as you can see, that pulsatile component has the inverse association with MoCA, but the mean component has the positive associations. And that observation was further confirmed by the multivariable model. After accounting for age, sex, education, depression score, heart rate, fasting sugar, the carotid energy pulsatility index remain significantly associated with MoCA score. And if we separate them into the pulsatile component and the mean component, as you can see that the pulsatile component is inverse associated with MoCA score, but the mean component was positive associated with the cognitive function. And what about the concepts of impedance mismatch? As you can see, with increasing proximal aorta stiffness, which is measured by the aortic characteristic impedance, with increasing proximal aortic stiffness, there's an increasing trend of carotid energy pulsatility index, which means that the pulsatile component is more penetrating to the brain. And with increasing aortic reflection coefficients, there's a decreasing trend of carotid energy pulsatility index. So in first study, we use this graphic abstract to illustrate all the concepts. And as you can see that for the heart, when we generate stroke volume into the systems, and there are probably 10% of the blood flow is in the pulsatile component. And with that transmitted into the brain, about 1/4 of the energy was transmitted into the brain. And only 4% is in pulsatile component, which means that our systems can buffer, especially in the end organ. They will use the carotid artery to buffer, to dam the pulsatile component. So with mean energy, the proportion is increasing and the pulsatile energy is decreasing. And as you can see that the positive component is negative associated with cognitive function, but the mean energy is positive associated with the energy. And now we are conducting another ongoing cohort. We want to evaluate not only the cognitive function, but also their renal functions. And in these projects, this is the concept map. We use the pulsatile energy and also the inflammation. I will not discuss in this, but for the pulsatile component, we will evaluate also their influence on not only the cognitive function, but also on renal outcomes. So in the second study, we invite around 160 HD subjects into the cohort, and compared to the community cohort, as you can see, that the HD subjects are more elderly, and a higher proportion of hypertension and diabetes, high blood pressure, and increasing stiffness as measured by carotid femoral pathway velocity. And as you can see, that the proximal aortic impedance, this is the measure of proximal aorta stiffness, about twice of the community cohort. And CAPW is only increasing marginally. And for carotid impure impedance, they have similar data increase as well, but the increasing extent is similar to CAPW. And they are around 1/3 of population are cognitive dysfunction. The MoCA score in average is 26. And in this HD population, again, you can see the damping phenomenon from the pulsatile component generated from the heart in the ascending aorta. The mean flow is around 85 milli per second. And in the carotid artery, it's about only the mean flow decreased by 1/3. But for the peak flow, it's decreasing by about 40%. So in turn, that the energy pulsatility index in aorta is 1.16, and for the common carotid artery is half, only 0.08. And there are some sex difference. And for all the hemodynamic parameters demonstrated in this figure, you can see the contrast between the HT population, CKD population, and normal population. And as you can see that energy pulsatility index decreased by 50%, but in normal population, it decreases by 64%. So it means that our HD subjects, their artery resistance cannot decrease the pulsatile component as efficiently as normal subjects. And as you can see that we mentioned earlier that the proximal aortic stiffness, the ascending aorta stiffness, is about twice of the normal subjects. But for the carotid impure impedance and CAPW, they are increased, but the increase extent is not as high as the proximal aortic stiffness, which means that in HD subjects, the proximal aorta is stiffened more than the whole artery system. And as you can see in this association analysis, that of all hemodynamic parameters, that the pulse pressure, energy pulsatility index, and are significant associates in a multivariate model with MoCA score. And if we separate that into the two components, mean energy and pulsatile energy, you can see that the mean energy is positively associated with MoCA, but the energy pulsatility index is negative associated. And in that analysis, we also conducted a competition multivariable regression analysis. As you can see that the carotid energy pulsatility index, even after accounting for the flow pulsatility index, or LT energy pulsatility index, or even the brachial pulse pressure, they remained significantly associated with MoCA score. Very interesting, you can see that if we put carotid mean energy and energy pulsatility index into the model, they both exist. So it means that there are two different different components. And how about the energy pulsatility index in relation to renal function? Again, we use the same cohort, 1,800 subjects, to evaluate their association with the renal function. As you can see in the right column, we use the different kind of hemodynamic parameters and to evaluate their association with renal function and left ventricular mass. As you can see, that carotid energy pulsatility index remains significantly associated with renal function. And if we use the ordinal logistic regression analysis, we categorize them into 5 categories and adjusting for age, sex, and body mass index. The carotid energy pulsatility index remains significantly associated with the renal function. And we further invite around 200 subjects in our studies as a CKD populations, and we use the general population as the contrast, so that will help us to evaluate the difference between them. And so we, for subjects with CKD, as you can see that they are elder, and the blood pressure are higher, and they have a lower renal function and decreased LVEF, also are in normal range, and higher LV mass. And for their plasma artery stiffness, about twice. And the CFPW increase a bit, around 3 increase. So how about the difference between all the hemodynamic parameters between the renal function subjects and renal dysfunction subjects and normal subjects? So you can see they have higher blood pressure, pulse pressure, and they also had a higher pulsatile energy and energy pulsatility index, either in ascending aorta, also in carotid artery. So in the association studies, we evaluate all the hemodynamic parameters. Again, that the energy pulsatility index are significantly associated with renal function, eGFR, either in ascending aorta or in the common carotid artery. And interestingly, the conventional hemodynamic measures such as LVEF or CFPW are not associated with renal function in our study. And in the multivariable analysis, we can see that the carotid, the LT energy pulsatility index and the carotid energy pulsatility index are significantly associated with reduced renal function in the logistic regression model. And we further invite some subjects to conduct the renal artery hemodynamics. So we measure their pressure and flow and combine them into the energy pulsatility measures, such as pulsatile mean energy and energy pulsatility index. And in that subset of studies, we can also see that the renal artery mean flow, peak flow, and flow pulsatility index, and all parameters are associated with renal function in the univariate. But in the multivariable model, adjusting for age, sex, BMI, DM, and hypertension, the energy pulsatility index remains significantly associated with eGFR in the renal artery. So, ladies and gentlemen, in conclusions, energetic hemodynamic parameters overall were more significantly associated with cognitive function and renal function than conventional pressure or flow-based parameters. And increased pulsatile energy and increased energy pulsatility index in both carotid and renal arteries are detrimental to cognitive function and renal function. And we demonstrate the concept of impedance mismatch with higher proximal aortic stiffness and the resultant rewarded aortic impedance mismatch. We can observe that there are an observation of excessive pulsatile energy across the aorta-carotid interface into the carotid artery, and which can result in the higher carotid energy pulsatility index, and then has the stronger association with the lower cognitive scores. And I will use this slide to thank all the investigators in this research teams to conduct a series of studies. Thanks for your attention.